Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be doing Form 3 Chemistry. And our topic for today is gas laws. So, today we are going to be focusing on Graham's law. So, in the previous lesson, we looked at combined gas law. You can go back and check that out. So, for today, we'll look at Graham's law and then we'll get a chance to practice a few questions. So diffusion is a continuous random motion of gases. The continuous motion usually differ from one gas to the other. So when molecules move from a region of high concentration to a region of low concentration, we usually refer that to as diffusion. So the rate of diffusion of a gas usually depends on its density. Basically, density is directly related to mass. Like the higher the rate of diffusion, the less the dense the mass. So we say that substances that are lighter, like very light, they usually diffuse at a very high rate of diffusion. They move faster. Substances that are very heavy, they do not move that fast. If you compare dust particles, like the small particles with air particles, you notice like the density of these small particles, the way they move from one place to the other in the room is at a different rate. Same case, like if you look at a gas and a liquid, and the way these particles move is completely different. The gases are less dense, they will tend to move faster. The liquids are denser in comparison to gases, they'll move slower. We are going to be comparing purely gases in this law. We are not going to be looking at liquids. The density of a gas depends on its relative molecular mass. So the higher the density, the higher the relative atomic mass, thus the lower the rate of diffusion. So you notice even when we are deriving the formula, you notice you use density as uh, one of the uh, whatever we are going to compare with, and also we are also going to use the atomic mass as well in our derivation of the formula. So, for example, if you look at carbon dioxide, it has a molecular mass of 44. We get this molecular mass by adding the atomic masses of each element. So, like if you look at carbon dioxide, we will take the atomic mass of carbon, the atomic mass of oxygen, and the atomic mass of oxygen. So, the atomic mass of carbon is 12, the atomic mass of oxygen is 16, the other one is 16. So, the total gives you 44 grams. So, and nitrogen, which has the molecular mass of 28. So, if you compare carbon dioxide and nitrogen, you notice carbon dioxide is very heavy, or it's denser. So, it is going to diffuse less, while nitrogen, which has a molecular mass of 28 grams, is less dense, so it will diffuse faster. We also take another example of ammonia, which has a molecular mass of 17, and nitrogen, which has a molecular mass of 28. You notice that nitrogen will diffuse like twice. It's twice lighter, so it means it will diffuse twice faster than ammonia. So ammonia has a molecular mass of 17, and hydrogen chloride gas has a molecular mass of that 6.5. Both of the gases when you put these gases together, they react to form white fumes of ammonium chloride. So this is an experiment to show like how density affects the rate of diffusion. So if ammonia was placed in one side of the a tube, and hydrochloric acid was placed in another side. Remember, we said ammonia has a molar mass of 17 grams, and then hydrochloric acid has a molecular mass of that 6.5 grams. So we notice that these two are going to react to form ammonium chloride, and you said these ones are white fumes. But you notice these white fumes are going to form much, much, much closer to where the hydrochloric acid is. So you notice some white fumes here. Why is it forming closer to hydrochloric acid? You notice for the ammonia, it moves really fast. So by the time it's meeting up with the ammonia to form ammonium chloride, the hydrochloric acid will not have moved at a larger distance because it's very heavy in comparison to our ammonia gas. So that is basically what we have explained. So hydrogen chloride is heavier while ammonia is lighter. So ammonia will diffuse faster. So the white fume will occur closer to where hydrochloric acid is, because hydrochloric acid do not move very fast. So the rate of diffusion is usually in accordance to the Graham's law of diffusion, which states that the rate of diffusion is inversely, note the word inversely, proportional to the square root of its density at the same temperature and pressure. So you notice when we are discussing Graham's law of diffusion, we do not talk about changes in temperature and pressure. The diffusion of these gases is calculated at the same temperature and pressure. So this is the law. The rate of diffusion is inversely, you can see the inverse, is inversely proportional to the density. So if we introduce the constant, remember we remove the sign of proportionality. When we have the rate of diffusion of two gases A and B, if you were to compare them, then we would say the rate of A is equals to the constant. Let's give it K over the density of A. So you give A the density of A. So if you have another gas, you call it the rate of B is equals to constant over the square root of density of B. So if you want to remove the constant in the first gas, that is gas A, we have to multiply the square root of density of A. So the constant is going to be the rate of A times the square root of density of A. And then the same case applies. So the constant in this side as well is going to be the rate of B times the square root of density of B. If we put the constant together, it means the rate of A, the square root times the square root, the density of A, square root of density of is equals to the rate of B times the square root density of B. So if you wanted to leave rates in one side, we can divide the square root density of A both sides. So, and then you divide by rate of B both sides. So we end up getting rate of A over rate of B is equals to, so the square root we can use 1 because it applies for both of them, density of B over density of A. So this gives us the first, in regards to the Graham's law of diffusion. So you notice that when you have the first rate, it's directly placed after. Then the rate of the gas B is placed afterwards. So this is the formula for density in relation to the Graham's law of diffusion. So once again, density, remember, is directly proportional to molecular mass. As we said before, they're directly related. So if there's a higher density, it means there is a higher molecular mass. So we can say that the rate of diffusion is inversely proportional to the square root of the molecular mass. So if you were to compare the rates of A and B, we will do the same case. So rate of A is equals to constant over the square root of molecular mass of A. We want to be left with constant one side. It means it's rate of A times the square root of molecular mass of A. If you had another gas, rate of B constant over the square root of the molecular mass of B. So if you want to be left with constant, it will be rate of B times the square root molecular mass of B. If we put the constant together, because it's constant either way, if we equate them together, it's going to be rate of A times the square root molecular mass of A is equals to rate of B times square root of molecular mass of B. If we want to be left with the rates, one side we multiply both sides by rate of B. So this cancels this. If you want to remove this molecular mass, we do the square root of molecular mass of A. This one cancels with this. You do the same case also this other side. So we end up having the rate of A over rate of B is equals to the square root molecular mass of B over molecular mass of A. So this is the formula in relation to the rate of diffusion to the molecular mass. Once again, when you take, it's possible to compare time taken for equal volumes of two gases to diffuse under the same conditions. So when you look at the time, these ones are not, it's not directly proportional to the mass. So for example, if you look at an heavy gas, for example, it will take less time. So you can see it doesn't go directly. It's not heavy taking like more time. Like it will take, if it is lighter, it takes less time to move across or to diffuse across. If it's heavy, it takes more time. So the rate is usually inversely proportional to time. They go opposite. So when we look at this formula, so we want to introduce the constant. So it's going to be rate is equals to K over time. So if we take two gases, for example, if we compare two gases, so we call it rate of A is equals to constant over time A. And then if you take another gas, rate B is equals to constant over time B. So if you want to be left with constant both sides, this is going to be rate A time A is equals to constant. And this is going to be rate B times B is equals to constant. If we put a constant together, it's the same as rate of A times of A is equals to rate of B times of B. If we want to be left with rates one side, we divide both sides by rate of B, and then again we divide both sides by rate of A, the time of A. So our final answer becomes rate of A over rate of B is equals to time of B over time of A. So this is another formula we can use. But then what we are going to do is just combine the three different formulas that we have come up with, and it's going to be rate of A over rate of B. We said the first one was the square root density of B over density of A, which is equals to the square root molecular mass of B over molecular mass of A, which is equals to time of B over time of A. So we can relate rate to density, we can relate rate to molecular mass, and we can relate rate to time. So we are going to use these three formulas the way we have written, depending on what you have been given in a question. So example, so let's do a few questions in regards to this formula. So how long would 200 centimeters cubed of hydrochloric take to diffuse through a porous plug if carbon dioxide takes 200 seconds to diffuse through? So the first step that you do before you start the calculation is to determine what you have and what are we supposed to look for. So when you look at what you have been given, we have the volume of hydrogen. I'm just going to write that. This is going to be our first gas, hydrogen chloride. So the volume is 200 centimeters cubed. The formula of hydrogen chloride is HCl. If you were to calculate the molecular mass, it would be the molecular mass of hydrogen plus the molecular mass of chlorine. So the molecular mass of hydrogen is 1, the molecular mass of chlorine is 35.5. So the total molecular mass is going to be 36.5. And then how long will it take? How long would 200 centimeters cubed of hydrogen chloride take? So basically, we have been told to look for the time in which hydrochloric acid takes to diffuse. So what else have we been given? We have been given something to do with carbon dioxide. So we have been given the time of carbon dioxide that it takes to diffuse. So we are going to write like this. So the time the carbon dioxide takes to diffuse is 200 seconds. And from the formula, we can also be able to calculate the molecular mass of carbon dioxide. So we'll take the atomic mass of carbon plus the atomic mass of oxygen. So the atomic mass of carbon is 12, oxygen is 16, another oxygen 16, which will give us 44. So looking at what we have, this helps us to know which formula we are going to use. So when you look at what we have time and molecular masses that we can use. So we can use the molecular mass and time formula, which goes as, remember what we said, molecular mass of B over molecular mass of A is equals to time of B over time of A. So that is the formula we use. So B is a second gas, A is a first gas. So in this case, we can start with the time. So we'll start with the time of the second gas, which is carbon dioxide, over time of the first gas, which is HCl, is equals to the square root of the molecular mass of the second gas, so the molecular mass of carbon dioxide, over the molecular mass of hydrochloric acid. So let's put the values we have now. So the first time of carbon dioxide we have been told is 200 seconds. The time for HCl is what we're actually looking for, is equals to the square root of the molecular mass of carbon dioxide is 44 over the molecular mass of hydrogen chloride is 36.5. So for us to remove the sign, we can continue the calculation as it is. We can do the division. So 44 divided by 36.5 will give us the square root of 1.2055, which is equals to 200 over time of HCl. So we can decide to do this square root, or we can remove the square root sign. So either way, we are still going to get the same answer. So if we do the square root of 1.2055, you get 1.09795, which is equals to 200 over time of HCl. So we can cross multiply so that we can be left with the time of HCl. So time of HCl is going to be, so if you multiply, it's going to be times 1.09795 is equals to 200. So time of HCl, it means you have to divide 200 by 1.09795. So the time for HCl will be 200 divided by 1.09795 will give us, 182.158 seconds. So that is the answer. I hope you have been able to see how we incorporated the formula. Let's do one more question. So it takes 30 seconds for 100 centimeters cubed of carbon dioxide to diffuse across a porous plate. How long will it take for 150 centimeters cubed of nitrogen dioxide to diffuse across the same plate under the same conditions of temperature and pressure? And we've been given the atomic masses. So let's record what we have. So we have time of CO2, which is 30 seconds. We have also volume of CO2, which is 100 centimeters cubed. And then we can also get the molecular mass of carbon dioxide, which we did in the previous example, which gave us 44 grams. And then how long will it take 150 centimeters cubed of nitrogen? So time of nitrogen, NO2, is equals to 150 centimeters cubed. And then we also can get the molecular mass of nitrogen dioxide, which will give us nitrogen plus oxygen, which is 14 plus 16 plus 16, which will give us a total of 46 grams. And so for the nitrogen oxide, we have the volume and the molecular mass. We don't have anything else. We do have the volume of nitrogen oxide is 150 centimeters cubed. So there are two ways you can be able to do this question. So I'll show you the first method, which is the very common method that most students tend to use. So you notice that these gases do not have similar volumes, and they have also different, you can see the question is how long will it take nitrogen oxide to diffuse across the porous plate. So basically we are looking for time. This is volume. We are looking for time of nitrogen oxide. So, but we cannot be able to relate the rate at which they diffuse without giving them like equal volumes. You notice for carbon dioxide we have 100 centimeters cubed, for nitrogen is 150. So there is no way we can use these volumes to get like the diffusion is going to be totally different. So you want to equalize them. So what you'll do, we are going to equalize the carbon dioxide to have the same volume with nitrogen oxide. So we'll say if 100 centimeters cubed of carbon dioxide diffuses for 30 seconds, what if we had the same the same amount of carbon dioxide that is in the nitrogen oxide? What I mean is, if we had the same values of the volume. So what about 150? Instead of using 100, so that we can be at the equal ground both for carbon dioxide and nitrogen oxide, so we equalize the volume. So if 100 centimeters cube of carbon dioxide would diffuse for 30 seconds, what about 150 centimeters cube of carbon dioxide would diffuse for how many seconds? This way now we are working from the same volume of carbon dioxide and volume of nitrogen oxide. So when we cross multiply, it's going to be 150 times 30 divided by 100, which gives us 45 seconds. Now we can use this time, it equalizes the question. So we are looking for time. So we'll start with the second. This is time of nitrogen oxide over time of carbon dioxide is equals to, we use the molecular mass because we have it. So the molecular mass of the second, which is nitrogen oxide, over the molecular mass of the first, which is carbon dioxide. Now we have time that is under the same volume. That way now we can be able to do the calculation. So the time for nitrogen oxide is what we are looking for, over carbon dioxide, which we got 45 seconds, is equals to the molecular mass of carbon dioxide, nitrogen oxide is 46, over the molecular mass of carbon dioxide is 44. So let's work out the values in the square root. So we are going to say 46 divided by 44 and do the square root, which is going to give us, so time of nitrogen 4 over 45, which will give us, so the square root of 46 divided by 44 is 1.02247. So if you want to be left with time for nitrogen oxide, you multiply by 45, multiply by 45 this other side. So this will give us the time for nitrogen oxide as 1.02247 times 45, which will be 46.01115, which is basically 46 seconds. So alternatively, we can decide to use the information that we have been given on carbon dioxide and get the rate. So we can look for the rate of carbon dioxide. The rate of carbon dioxide will be the volume. We do the volume over the time taken. So the volume for carbon dioxide was 100. The time taken was 30, which will give us 3.333 centimeters cubed per seconds. That is the rate. So in our formula, we are going to use this now. We will say now the rate of carbon dioxide over the rate of nitrogen dioxide is equals to, we still use the molecular mass 46 over 44. Let me put that as the numbers. So molecular mass of nitrogen dioxide over the molecular mass of carbon dioxide. So that's what we wanted. So remember now we have rate of carbon dioxide, which is 3.33 3 over the rate of nitrogen dioxide, which we do not have, is equals to, we had initially calculated the molecular mass of nitrogen dioxide as 46 and the molecular mass of carbon dioxide as 44. So this will give us the square root of 46 divided by 44 will give us 1.0225 and then 3.333 over rate of nitrogen dioxide. So if we want to be left with nitrogen dioxide with cross multiply, so it's going to be 3333 is equals to rate of nitrogen dioxide times 1.0225. So you divide by 1.0225 both sides, which will give us that the rate of nitrogen dioxide is equals to 3.26 centimeters per second. So if you want to be able to now calculate the time it took for nitrogen dioxide to diffuse, remember we said rate is equals to, we use the volume over the time taken. So now we have the rate, which is 3.26 is equals to volume, which is 150 over the time taken. So we cross multiply, which will give us time taken for nitrogen dioxide to be 150 divided by 3.26. So if you divide that, it's going to give you 46 seconds, which is similar to what we got from the previous calculations. So that's how you calculate those values. So that brings us to the end of the session. You can check out more questions in the notes section so that you can get to practice. So see you in the next lesson.